Welcome back, everyone, to this second video of GATO, where we're going to talk more about the details of how we encode information. So in the last video, we went over the structure of GATO, and we looked at, for example, all of these different tasks that we're able to perform quite well on with the architecture. And one of the questions that came up was, how do we actually encode information from a variety of sources to make them compatible with the model? So for example, we're using text parsing here. So we have a task for GATO to maintain a dialogue, and we need some way of interpreting that data. But similarly, we also have, for example, performance on Atari games up here, where you need to look at an image and from that image come up with some suggested actions. So you have very varying forms of data, and you need some way of interpreting this. We also looked at the overall structure of GATO and the way we encode data, which you can see down here in a sequence of both observations and actions. Then we have some interpretation by the model and the environment to produce consecutive actions. But the moral of the story, or the key point that we want to take away, is that we're using a variety of relevant data to train the model. So we're using images, text, joint torques, button presses, and other forms of observations, and also varying forms of actions. So for example, if you want to respond to some sort of message, you would need a number of actions, just not, let's say, one word, but really a sequence of words that you need to put together. So we need some way of standardizing that and for the model to interpret it. And that's what we're focusing on in this video. First of all, we want to take a sort of high level view of this tokenization procedure. And you can see in the first box here, basically described how the input is interpreted by the model. So first of all, the episodes that we encounter are ordered just in terms of time. So really the only wiggle room, let's say, that we have in the model is within one time step. How do we order the different sequences in there? So episodes are ordered in terms of time, and for each time step, you have first the observations, then you have a special separator token that we can see here, and then you have the actions. So for each time step, you always follow that sort of procedure. And an illustration of one time step would then be illustrated here. So we have time step 1 is on the left side, and then time step T is here. And for each time step, you have these different observations, and then a separator token and an action. Now, these observations can be of a variety of different flavors. So we have all these different inputs, and we're going to discuss now, how do we deal with these, one-on-one. So we have the observations here, and they are ordered according to a particular key. The ordering is not that crucial. We're more interested in how do we interpret this data. So how do we get from an image, for example, to something encoded? So we have text tokens as one input. We have image tokens as another, and then we have tensors as a third flavor of inputs. And for all of these, our strategy is a bit different. For text tokens, we simply order these in the same order as the raw text, and we use sentence piece encoding. So sentence piece encoding, you can look that up in a separate video if you want to know more details. We're not going to go through it here, but nevertheless, the text is encoded and it's done so in a sequential order. I think that is the most clear of the inputs. When it comes to images, though, we need some way of appropriately treating those, and they actually split those up in something called raster order. I gave a quick highlight here of what that means, but we're going to look at it in more detail in a couple of slides. It essentially means, so row major order or raster order, they are essentially the same. It means that you go in a row-based manner across some sort of matrix like this. In the case where we have an image, this would mean that we actually split the image up into sub-images, but that's what we're going to look at more detail in the next slide. But just know that the order we're using is sort of row-based for both of these. Similar for tensors, then, we use this row major order. The separator token is not much to say. It's just a token to give the model knowledge that we're separating the observations now from whichever action you're taking. And then we have the actions themselves. And in case there are multiple actions associated with one time step, they would be ordered in row major order also. All right, let's discuss how these are encoded in more detail now. So we know the ordering, but that's not very interesting. What's more interesting is what we're going to talk about now, which is how do you go from a state representation, whatever that might be, to this flattened sequence of tokens. So we have a first example here, and this is the example of a tensor. So we have a state representation for this inverted pendulum that you can see to the top left here. We have 4 different dimensions that we're recording for this. They could be, let's say, velocity and position, information. And then we have one action, which would, be perhaps a torque to an engine or something like that. The first thing we do is we take these numbers that we get as input, and we encode those using what's called mu-law encoding and vector embedding. And we're going to go into detail of what this means, but once that's been performed, what we end up with is a set of vectors that you can see here. So each of these turn into an individual vector, also the action, and this is done in a particular way. Mu-law encoding is a way of limiting dynamic range of an input. We have a figure on that in the next slide, so I'm going to show you in just a second. But it limits, it makes sort of the input more appropriate for dealing or for being handled by a neural network. And what is then performed is a vector embedding, which turns these into vectors, as we said. And this vector embedding is done using a lookup table that's learned by the model. Okay, so that's the first step, and we're going to come back to the mu-law encoding and what that means. Once we've done this, they apply something which is called local position encoding. What that is a position index of each of these vectors that illustrate at what position within the time step this occurs. So we would normally have a number of observations and also a number of actions at the same time step. And this position encoding gives information about what position within the time step does this particular vector show up in. And the way that is done is first you assign an index to this, so just one through n, whatever n might be, like a big number. And based on these, you then also turn that index into a vector. So as you can see here, as an example for the position encoding, you have some sort of vector. This corresponds to the first vector in the sequence over here. And then we add some vector to that. Now, this would be the encoding of index 0. Similarly, the vector we add here would be the encoding of index 1. And these are also encoded using a lookup table that is learned by the model. The only exception here is that for actions, so in particular for the action, we always use the same index. So there's a special one reserved for the actions, and that doesn't change. So they always get the same encoding. Okay. And after that, we can then append these to the full sequence. And that's how they take the information from a state representation like this and get it into a flattened sequence that we can feed directly to the model. So with that, let's now look at the mu-law encoding in more detail and see what happens in that step. So what we do for pre-processing this before encoding into our vector space. Mu-law encoding is illustrated in the first part of this slide. We can see an input signal here. And the thing you should note is that the dynamic range varies quite a bit. So what we mean by dynamic range is that if you look at the first part of the sequence, it doesn't fluctuate very much, whereas here it fluctuates a lot. So the range of this signal varies over time, hence the dynamic range is quite large. And we want to reduce that. So what you can see on the right side is something that's been mu-law encoded, and you can see that the dynamic range of this is much smaller. So it has more of a it utilizes the entire range in a better way, which is important for a neural network, because if your signals vary a lot in, by several orders of magnitude, depending on where in the observation sequence you are, that could mean trouble for predictions. So that is what we're trying to do here. And there's a particular function that's used to transform one of these signals into the other. The parameters of that particular function are listed here, but I think the function expression is not as interesting as, the intuition for what this does. So it limits the dynamic range to make it easier for the model to interpret that particular input. In addition to this, they need to restrict the range of these in some way. So they cap it to the range of -1 or 1. So that's where they allow the range of a signal to be. And then they discretize this to a number of bins. I made a simplified illustration of what this means down here. So there's a ceiling, which corresponds to the level 1 here. And that's essentially where this process signal gets flattened out. And then in between here, there's some discretization, which means that we get this jagged behavior. Of course, since they have 1,000 bins roughly, it's going to be much more fine than the coarse sort of illustration I made down here, but the essential takeaway is the same for both of these. So that's what they do. And that's essentially how we encode a tensor. Now that we know that, let's move on to images as well. So we're not only interested in parsing tensors, but also images. And as I said before, we use raster order for these images, which is illustrated here. So what it means is we split the image up into a number of different sub images, and each of those is fed to the model separately in order to give individual pieces of this image the ability to be processed one at a time. And you can see the ordering that we put in place for the image here. And then we also have some sort of action that make it into the first stage of our input. So this is the tokenized data that we begin with. What we do then is we embed this representation into a vector space, very similar to before. And then we arrive at a final sequence after that, once we have added a local position encoding. So it's very similar to what we saw for the tensors, actually, pretty much exactly the same steps. Although in this step, where we go to the embedded representation, there are some question marks that we need to iron out. So we need some way of taking an image like this and getting to an embedded representation. And they use what's called a ResNet architecture for this. So that's what we're going to look at next. That's illustrated here. So what we can see as an input this time is one of these sub images. So it's not the full image, but really one of those sub images that we split up using raster order in the beginning. Now, the ResNet architecture is a separate paper altogether. I will link that in the description of this video. But essentially what it is based on are these kinds of blocks that can be stacked on top of each other. You have an input and then you have an output, and the input can flow directly through this sequence and make it to the output. But there is also this other track that it can pass through and gets added to the original sequence here at the end. So there are two paths that the information can flow through this model. This more interesting part of it on the right-hand side here is comprised of different blocks. So we have first a group norm, then a GELU, and then a weight. And we have two of these stacked onto each other. So then we have the same sort of architecture repeating itself again. For these different ones, so group norm is a way of normalizing the data. So similar to what we saw for the mu law encoding, this would change things to become appropriate in scales. And this is sort of a mix between layer norm and instance norm, if you're very familiar with different normalization strategies. If not, then I think it's fair to say that this is just normalizing the scales of the input. What comes next is an activation function, namely GELU. So activation functions are widely used in these kinds of applications. And this particular one is good in the sense that it adds some non-zero range here. So for most, like a reload function, for example, would be flat in the first part here. And then after we cross this boundary, you would have some linear behavior. Here you have a descent right before that switch, and then it goes up, back up. And what this does is it prevents some of these nodes in the network to die out when we do back propagation. It's a technical detail, but that's the reason why not a standard relo is used in this particular application. Then we have a weight layer, and the weights are configurable hyperparameters, and they are normally convolutional layers in the application. As you're probably aware, convolutional layers are useful for parsing images. So, you know, it's kind of a natural choice in this case. And that's what you use to comprise this network. And based on that, these would then get trained during, training of the model, and it would learn to then produce these vector outputs. And so taking that back to the previous slide, we would see that for one application of each, we would get one vector like this, and then we can add a position encoding to get to the final sequence. For the embedding of these images, it's, a bit more interesting than before. So what we do is we have these image patches, right? So these would be the same as the original raster order. And for each one of these, we record both the X coordinates and the Y coordinates, and we normalize those to the range of between 0 and 128. So each one of these would get a value between, the starting point and the finish point normalized between 0 and 128. And for training, the local position index that would be used would be the center point of each one. That's illustrated here. So in this case, for this particular image patch, you would get 64 and 48 as the positions in the index. But during evaluation, they use a random point in the range. They don't mention exactly why in the paper. That would be something very interesting to know. So if you have an idea there, please put that in the comments, because I would be interested in knowing. Nevertheless, they use a random point during evaluation for the model. And with that, you can get the standardized encoding. And that is essentially how the encoding works for GATO. So that's it for today. Stay tuned for the next video, and thanks for watching.